Good morning, sir. I'm Charita from ECE. I'm pursuing my BTech first year in Srinivasa Ramanujan Institute of Technology. So today I'm here to explain about Hall effects. Before entering into the topic, I'm going to give a brief explanation on Hall effects. When a piece of semiconductor carrying a current placed in a transverse magnetic field, an electric field is produced inside the conductor in a direction perpendicular to both current and magnetic field. This phenomena is known as Hall effect and the generated voltage is called Hall voltage. Let us consider a rectangular slab of uniform thickness T, width W and length L placed parallel to x-axis. A current I passing through a plate along the x-axis. The magnetic field is applied along y-axis. The force is experienced along z-axis as shown in the figure. Due to this Hall voltage, potential develop at two ends of this plate. For n-type semiconductors, the force will be along z-axis. So, the electrons are accumulated on the upper surface of the plate. For p-type semiconductors, holes are accumulated on the upper surface of the plate. So, coming to the Hall electric field. The force experienced by the charge carriers due to the electric field is known as Hall electric field. What is meant by Hall coefficient? It is the ratio of Hall electric field to the product of current, density and magnetic induction. It is denoted by RH. Coming to the applications of Hall effect. The sign of the Hall coefficient can be used to determine whether a given semiconductor is n-type or p-type. For n-type, Hall coefficient is negative. For p-type, Hall coefficient is positive. It is used to calculate the number of charge carriers, the mobility of the electrons. It is used to measure the magnetic flux density and the drift velocity. So, introduction to Hall effects. Hall effects refers to the generation of voltage across a conductor when it is placed in a magnetic field. This phenomenon occurs due to the Lorentz force acting on charge carriers within the conductor. Hall effects are widely used in various applications including sensors and measuring devices. Historical background. The Hall effect was discovered by American physicist Edwin Hall in 1879. Hall measured the voltage difference across a thin gold film in the presence of a magnetic field. This discovery laid the foundation for further research in electromagnetism and semiconductor physics. Basic principles of Hall effect. The Hall effect arises when charged particles experience force due to a magnetic field perpendicular to their motion. As the charge carriers move through a conductor, they are deflected, leading to a voltage difference across the material. The resulting voltage is known as the Hall voltage and is directly proportional to the magnetic field strength. Mathematical representation. The Hall voltage VH can be expressed by the equation VH equals to IB by NQ, where I is the current, B is the magnetic field, N is the charge density, and Q is the charge of the carriers. This equation highlights the relationship between current, magnetic field, and the charge carrier properties. Understanding this equation is essential for designing devices that utilize the Hall effect. Here is the mathematical representation of Hall coefficient again, where RH equals to EY by ZX into BZ equals to VHT by IX BZ equals to 1 by NE, where EY equals to induced electric field in Y direction Hall electric field, VH equals to Hall voltage, Zx equals to current density of the charge carriers, that is electrons in x direction, drift velocity of the current in xy direction, that is Vx, Bz magnetic field in z direction, Ix electric field due to DC supply in x direction, W width of the conductor, T thickness of the conductor, where N equals to number of charge carriers, E equals to charge of electrons. Types of Hall effect. There are two main types of Hall effects, classical Hall effect and quantum Hall effect. The classical Hall effect applies to conventional conductors and semiconductors, while the quantum Hall effect occurs at low temperatures and high magnetic field. Each type has unique properties and applications in technology and research. Applications of Hall effect. Hall effect sensors are commonly used in automotive applications for detecting position and speed. These sensors play a vital role in anti-lock braking systems and electric stability control. Additionally, Hall effect sensors are used in industrial applications for current sensing and motor control. Advantages of Hall effect devices. Hall effect devices are non-contact, meaning they can operate without physical contact with the measured object. They provide high precision and reliability in various environmental conditions. Furthermore, Hall effect sensors are compact and can be easily integrated into electronic systems. Limitations of Hall effect. One limitation is the sensitivity to temperature changes, which can affect accuracy. Hall effect devices also require a minimum magnetic field strength to operate effectively. Additionally, the linearity of the output can be affected by the geometry of the sensor and the material used. Future trends in Hall effect technology. Ongoing research aims to improve the sensitivity and range of Hall effect sensors for advanced applications. The integration of Hall effect technology with IoT devices is anticipated to enhance smart sensing capabilities. Innovations in material science may lead to development of more efficient Hall effect devices. Finally, conclusion. The Hall effect is a fundamental phenomenon with significant implications in physics and engineering. Its applications span various industries, contributing to advancements in technology and automation. Understanding Hall effects will continue to be essential for future innovations in electronics and material science. Thank you.